Morning, everyone. Thanks for coming. My name is Mohamed. I look after HVAC product sales at Jonson Controls, and today we're going to talk about heat pumps and the road to decarbonization. So, called the decarb conundrum. Why decarbonize? Well, we got targets to meet: 2040, 2050, 2030, whatever the case may be. But more importantly, it's good for the environment, and we want to leave the world a much better place for our older selves and future generations. What do we decarbonize? That's defined by your scope 1 emissions, which is direct company, facilities and vehicles. Scope 2, which is where do you get your power, energy and cooling and heating from. And scope 3, which is your indirect upstream and downstream activities, which tend to have a carbon imprint based on how you choose to use your supply chain, up or down. How do we decarbonize? It's quite simple, really. So you improve efficiencies. So in the building envelope, your lighting, your appliances, use more efficient equipment. Electrify everything. So your heating, cooling, cooking, where you get your power from. And of course, phase out fossil fuels. So anything you use burning to get an output of heating, hot water, cooking, phase out all of that. Quite simple. And a big part of the how is heat pumps. General overview. So they have been around for many years in terms of applications. We've got commercial, industrial application units. Because of the concern to environmental impact, heat pumps are now being developed with low impact or global warming potential refrigerants, and transitioning from that to zero or natural refrigerants without any environmental impact. We've got a large range of air source heat pumps and water source heat pumps. So depending on the kind of application that you're using, if it's a single unit, individual usage, zonal usage, or even large plant central equipment, we've got the range to meet all of these requirements. So these can deliver anywhere from 5 kilowatts to 5 megawatts of heating, delivering temperatures between 45 to 130 degrees. Again, depending on the application that you're looking for. Versus a boiler, obvious benefits. So most important, it's more efficient. So a unit of gas would give you 0.95 units of heat, whereas you get about 4 to 5 units of heat from a unit of electricity that's pumped into the heat pump. Reduce carbon emissions. So it's a direct impact on scope 1, which is the facilities. And of course, lower operating and maintenance costs. So you have reduced expenditure on fuel, storage and equipment maintenance. How does it operate? So if you power up a water source heat pump with a unit of electricity, it takes about 4 to 5 units of heat from the source and delivers 5 units of heating output. For the air source heat pump, that same power electricity, because it's because the medium it takes the energy from is a lot more inefficient, you get about 4 units of heat output. And this is your season across the board. So typically these units are designed for a single point, worst case scenario. But 4 units of heat output is across the board on a year-round operation. Applications. So typically you would find a boiler replacement project. So in the old facilities you might have separate loops for both heating and cooling. So what we find is if you can take return water from the chill water loop and return water from the hot water loop and run it through a heat pump, you can deliver lower temperature, 7 degrees onto the chill water loop, and deliver up to 65 degrees on the hot water loop, which you can then use to bypass your boiler and eventually phase it out. An offshoot benefit of this is that since you're sending lower temperatures to the chill water return, your chillers will actually perform more efficiently. So instead of cooling from 12 to 7, you might end up cooling from, because it's a mix, you might end up cooling from, let's say, 9 or 10 to 7. So it's an impact on your overall heating or cooling system efficiency. Waste heat reclaim. So typically your chillers would reject heat into a cooling tower, which is then just dissipated into the atmosphere. So that's energy just wasted. If we plug in a heat pump onto that condenser or heat rejection line, you can actually deliver hot water temperatures up to 80 and completely offset your boiler. So another example of using heat or energy that was otherwise wasted and bringing it back into useful application. Simultaneous heating and cooling. So this is a 4-pipe air source heat pump product. So from the same unit, depending on what time of the year it is, you can get cooling only, so it rejects heat into the atmosphere. You can use it for heating only, so it draws heat from the source and utilizes for heating. And as in the case in most of the facilities here, you will have times when you need both heating and cooling in the same building. So that same unit can give you both heating and cooling, transitioning the energy from each circuit and driving the efficiency of this particular equipment all the way up to 8, 9. So from a single unit, you can get year-round heating and cooling, and you may need a boiler depending on the kind of temperatures you have, but you would use it very sparingly or not use it at all, depending on the system design. Benefits versus implications. So obvious benefits: lower running costs, higher operating efficiencies, zero carbon emissions, year-round heating and cooling, long lifespan and lower maintenance cost. As with any equipment, you will have pitfalls. So you need space to install all these items or these equipment. You need the power to run them. Depending if it's an existing site, that could be a struggle. Higher energy costs. So unit price of gas versus unit price of electricity. Because of that difference, it might offset the actual benefit of implementing the system. And the refrigerants that are typically used in heat pumps do have an environmental impact, although it's not as bad as burning fuel. Implementation, one of the key things that we want to discuss is, so what we understand is there are typical pain points when deciding to do a decarbonization project. So site-related constraints such as space, power, access, existing system constraints on set points. So will the new system actually meet those existing requirements on site? Challenges during implementation, I can do a whole session on that. Budget and time constraints versus there is pressure to implement the latest, most energy efficient systems. And will the system actually meet set targets related to performance and ROI? And the very important question is, who's going to pay for all this? Carbon Energy Fund, of course. So I got road to decarbonization. There's a method to this madness, as they say. So if you follow a step-by-step process, you are more likely to succeed than fail in your road to decarbonization. So one is to have that idea, that concept of, yes, to implement a decarbonization plan. Once you've decided on that, we do what is called as a heat mapping. So understanding where the heating and cooling loads are, what points in the building, and do a site-specific requirement capture. Then we do a detailed project design, plus select the right product for that particular application. And of course, install and commission the plant. And one of the most important things that tends to get overlooked in all of this is maintenance of the plant. So you can't have any of this working in silos. All this has to work together. So these are connected, and anything that works in isolation will end up derailing the whole project altogether. A few case studies that we've done. So St. Michael's Hospital in Toronto, fairly large facility, quite old. They managed to save around 1.4 million annually by retrofitting their existing system. So what we had done was we employed a technology using 2 centrifugal compressors, which in heating mode can give you 3 megawatts of heating, and also during that time it uses waste heat from the facility, and it also delivers your cooling. So by implementing this, they were able to save around $8,000 a day, 36% reduction in gas emissions or carbon emissions, and in achieving a COP of 4.2. 4.2 is very low because it's freezing in Toronto. You get temperatures of like minus 20, minus 40. So yeah, but still in those conditions we still achieve 4.2. Another example, not exactly healthcare, but showcasing some technology. Agro Muscater's dairy farm. So they had an aging facility which they wanted to refab, but their focus was to reduce energy and water consumption and also reduce carbon emissions, and they wanted to future-proof it. So what we did was a combination of a heat pump with a supercharged compression system and a buffer vessel. This is an engineered solution specific to that site, using natural refrigerant because they wanted to future-proof. They didn't want to have those environmental impact in the future. So we were able to double their savings, COP of more than 5 for that heat pump, and it resulted in about 10% more efficient operation because of that specific technology being used. Something closer to home, Salisbury Hospital. So that hospital is looking to offset carbon by replacing their existing boiler-based heating system. So we implemented an air source heat pump directly to heat the swimming pools. There was a high temp water system with water source heat pump, which was simultaneous heating and cooling. So you would get 75 degrees of hot water and 6 degrees of chill water from the same equipment. And this is about a megawatt of capacity. Plus we used a cascade system. So an air source heat pump, a buffer vessel, and a water source. So the air source would deliver the low temperature hot water system requirements of 45 degrees, and whenever required the water source would boost that up to 78 degrees. So with this, they actually achieved 914 tons of carbon reduction every year, 30,000 pound savings, not too much, but can't complain. And the combined system COP of this particular system implemented was around in the range of 8 to 10. So at the end of the day, implementing a decarb project with heat pumps does give you savings in different avenues. Any questions?
So, going back to the Salisbury project, in terms of the water source heat pump, 75 and 6 simultaneously?
Yeah.
Which refrigerant are you using?
1234 ZE. It's primarily linked to our VSD screw compressor technology.
Is it yours?
Yeah.
Quite interesting to see.
Yeah. Any questions? Thank you very much. So to know more, we are in stand E72. Please do visit if you need anything. Thank you. Thank you very much.
They are doing something similar.